We'll go over the Formula SAE Expo presentation for team number 33. Our team advisor for this project was Dr. John Christopher Bachman. The team members consist of David Arellano, Francisco Calva, Patrick Cho, Hector Coronel, Frank Garcia, Abel Moreno, Carlos Ochoa, and Erick Rojas. So for the agenda, the introduction will be done by myself, Frank. Driver controls will be done by Abel. Suspension will be done by David and Patrick. Powertrain will be done by Francisco, Hector, and myself. And electrical will be conducted by Carlos and Erick. So for the team objective, the senior design team this year was in charge of the Formula SAE project vehicle. This time we were in charge of the subsections of suspension, brakes, powertrain, and electrical subsystems for the team competition of 2020 to 2021. The team organization consists of the client, Formula SAE. The team advisor previously stated was Dr. John Christopher Bachman. Team captain was myself, Frank Garcia, with driver controls headed by Abel Moreno, electrical headed by Carlos Ochoa and Erick Rojas, powertrain headed by Francisco Calva, Hector Coronel, and myself, Frank Garcia, and suspension directed by David Arellano and Patrick Cho. So this is an isometric view of the overall car and the subsections integrated to the car. This is a top-down view of the same car with all components added onto one master CAD, as you see below. So now I'll pass it on to driver controls to Abel.
Thank you, Frank. So my name is Abel Moreno. I was in charge of driver controls, and right now you're seeing the pedal assembly. Everything else will be manufactured out of aluminum 6061 T6, except for the steel tabs that's going to be holding up the pedals. Next slide. The final components for my section was the shifter. We opted in for a left-hand shifter. And next slide. And right here is our brake pedal analysis. Due to some software limitations, we had to treat the pivot point as a fixed point. Because of that, it led to a safety factor of 1.89 with an applied force of 2,000 newtons or 450 pounds. And that is set by the Formula SAE rules. Next slide. Here we have the brake pedal kinematics. Gamma will be the angle between the brake pedal and the base, and alpha will be the angle between the master cylinder and the base. Ultimately, we calculated a value of 0.55 del C, and so but while the CAD simulated a compression rate of about 0.6 inches, we decided to go with our calculation, seeing how it was a bit lower. And we just wanted to make sure that we didn't overestimate the value. Next slide. So for our brake rotors, we decided to go with ASTM 836 low carbon steel. For the front rotor is about 8-inch in diameter, and the rear is 7-inch in diameter. This is to accommodate for the weight shift that happens while braking. It's also the reason why we chose two different calipers, the Wilwood GP200s for the front and the Wilwood PS1 for the rear, since the GP200s have a higher or greater piston area, which will allow for a greater braking force. Next slide. So here we have a thermal analysis for the front brake rotor. This is simulated under braking to get the wheels to lock. And as you can see, our desired the temperature reaches from about 206 to about 282. Degrees, which is well below the boiling point of top for braking fluid. Next slide. Here we have a second thermal analysis of the front brake rotor. This is to be simulated for the endurance track or the endurance portion of the competition. So this was more of a narrative process, also due to some software limitation. So the way we did this one was we set it up for 3 different laps. The first lap being the initial temperature of 75 degrees, which then resulted at a max temperature of 318 degrees, which was then used for the initial temperature for lap 2, and so forth. Ultimately, after lap 3, there was no dramatic change in the peak temperature that it ranged, since lab 2 resulted was 328 degrees Fahrenheit, and lab 3 resulted with 329 peak temperature Fahrenheit. Uh, but it still was in our desired range of 250 to 350 degrees Fahrenheit, which would allow our brake pads to reach a friction of 0.4 to 0.45. Next slide. And I will now pass it over to David and Patrick to talk about suspension.
Thanks, Abel. Hi, my name is David Arellano. I designed the front suspension, and Patrick Cho designed the rear suspension. This is the steering system that consists of the steering wheel, steering column, U-joint, steering rack, and steering linkages. All of this is designed to maximize friction, roll, and stability with the ground. Next slide. This is the rear suspension. It's very similar to the front. The only difference is the steering system is now a fixed toe arm. This is also a similar pushrod system, except the rear is attached directly to the upright. Next slide. These are my overall specs that help me guide this year's design. Many of my design overall specifications revolve around the forces produced from my tire. The biggest change from last year's design was to change the front direct attachment to a pushrod system, matching the rear suspension. The weight budget and ride height were reduced to increase overall performance for this year. Next slide. These are my final design specifications that help fine-tune the suspension. These include steering geometry, ride frequencies, motion ratios, and spring rates. Next slide. This is my final upright design, and on the right shows an exploded view. Next slide. And this is the final rear design, and on the right also shows the exploded view. And next slide. Now I'll pass it over to Patrick to talk about the FE analysis.
The FAA analysis for the uprights included using free body diagram analysis to determine the reaction forces at various points on the upright. The reaction points that we analyzed was the upper control arm mounting point, the lower control arm mounting point, as well as the push rod mounting point. Next slide. Once we determine the reaction forces at those locations, we plug this into SOLIDWORKS and use the FEA analysis tools to come up with the factor safety graphs as shown in the figures below. These figures show the upright during a cornering event where the vehicle is undergoing a tight turn. During these kind of scenarios, the upright will bend, and as such, there will be a massive amount of stress right near the center where the wheel hub and bearings are located, which is evidenced in the heat map shown below. Next slide. Similar analysis was done on the control arms. For the sake of time, this is the rear arm, the rear lower arm. As you can see, the max stress is done when the vehicle is cornering. When the vehicle is cornering, the A arms are under compressive load. Next slide.
This is the plan for testing for the future to verify our design. The method of recording this data will be to use a video camera, accelerometers, stopwatches, and temperature sensors. The testing will be done in the school parking lot. We expect to validate our max lateral force, max roll, and our operating temperatures of our tire. Next slide. Now I'll pass it over onto powertrain, covered by Francisco, Hector, and Frank.
My name is Francisco Calva, covering the intake and exhaust system with Hector Coronel. Next slide. The engine used this year will be a 2015 KTM 690 Duke, which is a single-cylinder engine with an engine displacement of 690 cc's. The goal for the engine was to produce 53.81 horsepower and 37.71 foot-pounds of torque. We hope to achieve our goals by optimizing our designs at 6,000 RPMs. Next slide. Starting off with the intake, shown is the overview of the system, where the air would flow in through the air filter into the throttle body, leading into the 20mm restrictor, which then moves into the plenum. Inside the plenum is a velocity stack, which leads to the runner and guides the air into the engine. Next slide. Listed are the design criteria. Packaging was important considering how we need to stay within an established intake envelope. The runner was optimized for 6,000 RPMs. We aim to increase the plenum volume to be greater than 1.5 times our engine displacement, which was 690 cc's. The specifications for the intake system are shown in the table. On the right, it is shown how we packaged our intake system, where the red lines represent the boundary of the specified intake envelope. Next slide. Starting with the 20mm restrictor required by the FSAE rules, shown on the table are the final dimensions, and shown on the right is the final design for the restrictor, where the fillet was chosen to be the best out of the 3 designs shown below. Next slide. The restrictor was chosen based on which one had the best pressure recovery using CFD analysis. The assumptions made for our simulation was that our system is working with 100% volumetric efficiency, meaning it provides 690 cubic centimeters of air into the engine. And we assume that our engine is running at 6,000 RPMs. The boundary condition for the inlet was atmospheric pressure, and for the outlet, it was a calculated mass flow rate of 0.0423 kilograms per second. Shown below is one of the pressure profiles for our analysis, where the background contours show the pressure readings and the arrows show the velocity of the pressure. The red signifies a high pressure and blue a low pressure. We wanted our restrictor to return to a high pressure towards the outlet. And as previously stated, the design with the fillet was shown to have the best results. And now I'll pass it on to Hector to cover the intake runner. Next slide.
So good afternoon, my name is Hector Coronel. I'll be discussing the runner length design, some of the components, some analysis and results that we obtained, and finally pictures of what we've been able to manufacture thus far. The runner length design is comprised of the 2 components, the velocity stack and the runner. The main objective of the velocity stack is to smoothly guide airflow as it's traveling down the intake system. Similar, the main objective of the runner is to also guide airflow while also being responsible for having the fuel to enter into the engine. Some of the measurements that we have to consider are the inner diameter, which was 1.86 for both components. And the material that we selected was aluminum 6061 T6. We chose the material because it's cheap, it's durable, it doesn't weigh much, and it's easy to machine. As for the length, we got 2.3 for the velocity stack and then 4.5 for the runner. Next slide. So in order to determine what the ideal runner length, we needed to analyze and research into a 4-stroke engine. There are 4 main parts of a 4-stroke engine, which is the intake stroke, the compression stroke, combustion, or also known as power, and then the exhaust stroke. We needed to analyze the camshaft duration and how long the valves will be open and closed. We can also note that during the 4-stroke engine, there will be 2 full revolutions, and then there will be pressure waves that will be traveling at the speed of sound, which is 343 meters per second. Next slide. After doing some testing and calculations, we were able to obtain results for intake and exhaust valves. For the intake valve, we concluded that during 2 revolutions, it will be open 228 degrees, and it will be closed for 492 degrees, and that the valve lid will be 0.420 inches. We did this by doing testing on the engine using a dial indicator and a degree wheel, as shown in the picture on the right. Then we were able to also obtain the location of the RPM of P power using a power band that we got from the manufacturer. We obtained that the peak engine power will be at 6,000 RPM. As for the runner length, we were able to obtain runner lengths at different RPMs and at different pulses. We concluded that the pressure wave at the 5th post would be more ideal, and that it would need to be at least 6.84 inches. Our final run length was 6.3 inches, so it satisfies it. Next slide. The following is what we've been able to manufacture thus far. For the velocity stack and the runner, we decided to make a prototype of how the component would look like once it's manufactured. We did this by 3D printing the component using PLA. For the runner, we already have it mostly manufactured using aluminum 6061 T6. We did this by using the lathe machine. However, we still need to manufacture the flange and then weld it to the runner. As for the velocity stack, we have yet to manufacture it, but we are planning using a CNC machine to manufacture the final component. Now I'll pass it back to Francisco. We'll talk about the exhaust.
Okay, moving on to the exhaust system. The main criteria was to incorporate the exhaust system into the side pods while optimizing the header length for 6,000 RPMs. We also wanted to choose a muffler that will allow us to reduce the amount of noise coming from the engine. The dimensions for the exhaust are shown on the table. The material used for the header was chosen to be stainless steel 304. Next slide. The length of the exhaust header was determined using the organ pipe theory, which has been shown to yield good results for a single cylinder engine. The equation calculated the length using the velocity of sound in gas, the crankshaft degrees, and the RPM. The table shows the calculated length to be 45 inches, but the actual length due to the packaging was 49.1 inches. Now Frank will talk about the cooling and fuel system.
Okay, now to go over the cooling system. So for the cooling system, as you can see, the picture on the left is just the radiator, and the picture on the right is the side pod with the radiator. And this was meant to show the integration of both the side pod with the radiator. So for the design for the cooling system, the criteria, as mentioned before, was integration with the side pod design, allowing it to be packaged with the side pod to be able to be used for prolonged use in static and dynamic events, and to keep the temperature of the engine below 257 degrees Fahrenheit. The specs for the cooling is a 10-inch diameter fan attached to the back of the radiator, and the radiator itself is an Austin Cooper radiator with the specifications in the table below. So as mentioned for the radiator itself is an Austin Rover Mini Cooper radiator, so it's a car radiator. The radiator itself is made of aluminum. The radiator internally has 2 rows, which allows for larger area of cooling, which means that the water has more surface area to hit, as it allows to propagate that cooling at a higher rate, allowing for colder water to enter the engine. The radiator itself can support the 10-inch diameter fan, which activates at a certain temperature to allow for even more cooling to happen as it pulls air through the radiator itself. So for some of the analysis done on the radiator, as you can see, radiator 1 is the Aston Martin radiator, which was compared against the power curve of the engine. So as you see on the right, the 2 graphs. So the power curve of the engine is just the engine itself on a RPM curve, and then this was plotted against the radiator being used along with the engine. And then the graph at the bottom is the temperature of the engine. So the temperature of the engine along with that power curve shows how much temperature the engine will be producing to the amount of temperature the radiator will be subtracting from that engine. So now for the fuel design. For the fuel system, the design criteria was just packaging and to be able to last the full endurance trek. As you can see on our table on the left, we have specifications for the fuel tank. The fuel tank will hold 91 octane fuel, which is standard fuel for the engine. The volume of the gas tank itself is 2 gallons, and the overall weight of the fuel system is 4.3 pounds. So for the fuel tank, as mentioned, is made of aluminum 5052, H32. The tank volume is 2 gallons, and this is based off the RPM given through a simulation through Adam's car. The internal components of the tank is 4 baffles to allow to minimize the amount of sloshing, to help the hauling mat, which is an internal fuel fuel filter to be able to absorb the fuel at a much steady rate. An external fuel pump will be used, which is rated for 40 to 80 psi, and it's mounted on the top of the tank to allow ease of use and to be able to be swapped out in case of any malfunctions. So for engine testing that will be done overall, some of the methods we'll be using is the use of a flow bench to test the restrictor and the intake system, an engine or chassis downer to mount up the engine to get an overall power curve and to see if whether or not some of the restrictor is performing as intended, temperature sensors for both the radiator to allow inlet and outlet temperature readings to be taken, a decibel meter to be used on the exhaust to specify if we're under the noise restriction, and a practice course. As mentioned before by suspension, it will be done at school. Our expectation is that this engine and the new mentioned parts will allow for the engine to reach a 53.8 horsepower and a torque of 37.71 foot-pounds. This will validate CFD. Engine will not overheat. We will have desired noise level, and we will have enough fuel to run for 13.2 miles, the length of endurance. And now I'll pass it on to electrical, which is both Carlos and Erick.
Thank you, Frank. Good evening, everyone. I'm Erick Rojas, and along with Carlos Ochoa, we will go over the electrical subsection. So to start off here are some of the specifications for the power distribution system. Some major factors that came into play was the battery. So by going with a lithium-ion battery, we were able to cut the overall weight by about 8 pounds, making the overall electrical subsystem around 11 pounds. Most of the power distribution system was stock, and we used factory recommended fuses and relays. The picture seen on the right are some of the enclosures implemented in the power distribution system. The fuse box seen on the top left picture holds up to 12 fuses and has its own ground bus, which makes it more space efficient. The picture to the right is the enclosure, which will hold the battery and the voltage regulator. And the last picture shown here is the power distribution holder, which will hold the fuse box, the 3 relays being the main relay, fuel pump relay, and the radiator fan relay, as well as have extra space for any microcontroller or any other component we would like to implement. Next slide. So here's the overall layout for the power distribution system. The battery and the voltage regulator enclosure will be placed under the seat, which will be surrounded by non-flammable material, and the power distribution holder will be placed by the front row hoop. Next slide. Next, we have some of the engine harness specifications. This harness was made to be modular, so as you can see on the picture to the right, there are 2 16-pin connectors. The total harness weighs around 8 pounds, and different gauge wire will be used depending on the component that will be attached to it. As you can see from the picture, all components will be separated to ensure that we have enough space to troubleshoot if needed. Next slide. So here we can see a simplified harness schematic. In this schematic, we can see different colored wires, which is key to having an understandable and organized harness. The red wire will symbolize power, white will symbolize the signal wire, green will symbolize signal ground, followed by black, which will be chassis ground. The symbol that you see on the right-hand side represents twisted wires, which helps mitigate impedances and noise in the signal wires. Next slide. So following each schematic page will be a legend. This legend will hold abbreviations to keep labels short and concise. And by labeling each wire, both EE and non-EE members will be able to troubleshoot the harness if needed. Now we'll pass it on to Carlos to finish off the electrical subsystem. Thanks.
Hello, my name is Carlos. So the ECU we will be using is the AM Infinity 506. The Infinity 506 has 80 pins, which gives us flexibility to add external sensors that we want to use for data acquisition. Our RPM sensor will be connected to the dash, which will be displayed along with LEDs for the driver so they know when to upshift or downshift. We will also have temperature sensors located around the vehicle, such as near the brake rotors and the engine. And the data that is collected from those temperature sensors will also be stored onto an SD card. Next slide, please. We have also documented the ECU pinouts for future teams. We have all the pins laid out and their purpose. we have the ones that are laid out for the ones that are being used and the ones not being used. We have also color coded this document with the colors that Eric mentioned earlier: red for power, white for signal, green for signal ground, and black for chassis ground. Next slide, please. So right here we have our placement for our temperature sensor on the upright. And as you can see on the picture on the left, it shows a distance of 1.13 inches, which is how far the temperature will actually be from the rotor, which is within the range of the sensor, and will read any temperature within that distance. Next slide.
If any questions are asked, please direct them during the executive summary.